All right, today let's take a look at some of the interesting things about areas and X circles. Let's begin with something that we're familiar with. If we have an ink circle inside a triangle, right? This is the ink center I. This is the ink radius, the radius of the ink circle, R. So how do we find R? Normally, we would take the area approach. A plus B plus C times R divides 2. That's the area of this triangle, and then this triangle. So basically, that should be the entire area of triangle ABC, right? And so if you know the three sides, you can use Heron's formula to get the area of triangle. And then you can get the ink radius, right? Not a problem. Now something similar could happen to our X circle. So the X circle here is drawn right here. Right, let's take a look. The radius, let's call that R1. Center at I1. Facing vertex A. X circle. Tangent to AB at point F. Tangent to BC at point D. Tangent to AC at point E. Do we still have some area equation or not? So actually, if we think about the area of this triangle, the area of this triangle is AB times the height R1 divides 2, right? And then the area of this triangle, that is AC times, again, the same height, R1 divides 2. If you add them up, that's basically the quadrilateral ABI1C, right? And so then you subtract which one? How about we subtract this one? If we subtract the area of this triangle, we will get ABC's area, right? So subtract that one. What's the area of this BCI1? That is half, again, the same radius, R1. Let me erase it here, right? Triangle BCR1 has base, BC height is R1, right? So now you notice that these three triangles have the same height, R1 dash. So we got an interesting thing going on here. So half R1 times AB plus AC minus BC, that should equal to the area of triangle ABC. All right, and then what is this? This is C plus B minus A. And if you are taking a closer look, half of C plus B minus A, that is exactly S minus A. All right, that's what we derived last time. How we get the, how we can calculate the radius of the X circle. But this time we proved it from area method. The interesting thing here is because of these three triangles sharing the same height, because of the tangent condition, that circle tangent to three sides. It's a pretty strong condition, right? Now, if you take another look at this formula, does that because it's saying that RA times S minus A. S minus A. What's S minus A? If you draw a ink circle, you will know what's S minus A. Let's take a closer look in the next picture. So if you draw the ink circle of triangle ABC, then this is S minus A. This is S minus A. The previous formula says S minus A times this RA equals what? The area of ABC. This green quadrilateral AG IAF, its area, if you think about it, what's the green one's area? It's this base times this height divided by half, which is this triangle. But then left and right, they are congruent. All right, multiply by 2. So that's exactly what we're going to get. The area of this green quadrilateral is S minus A times RA. That equals the area of triangle ABC. So it's saying that this green quadrilateral's area is the same as the triangle ABC. It looks interesting and suspicious. Can we give a different proof for this? I suppose we can give it a shot. Now, let's think about it. The area of this triangle, I can take a different approach to calculate. The area of this triangle is half S minus A, this side, times this long leg, A, IA, times the sine of this angle, half A. Right? If I give you a triangle with A and B here, this is angle C, then its area is half AB sine C. That's what we do here. So for the green one, the quadrilateral, it's twice of that. So I can remove that. So the area of this quadrilateral is supposedly equal this, but what's the area of triangle ABC? But this time I'm going to also try to use this angle bisectors property. So I'm going to calculate the area of ABC using two parts. This part and then this part. Right, let's try that. That is supposedly equal to half AB times AJ times sine half A plus half AC times AJ times sine half A. So if you add them up, we will get half AJ times sine half A, AB plus AC. So we are thinking maybe these two are equal. Can we prove that? Can we prove this from a different perspective? So let's cross out some common terms. This is crossed out. So S minus A times AIA. I want to prove this equals AJ times half of what? C plus B, B plus C here. And allow me to change the notation a little bit. So we're trying to prove that AJ divides AIA equal S minus A is half B plus C minus A divides this term, half B plus C. It should equal to B plus C minus A divides B plus C. Interesting. Is that correct? So I want to prove this equal this. Can we do that? Is that right? Does this equation hold? What's AJ again? The angle bisector right here, touching BC. Think about it for a moment. Can you prove that? Actually, to do that is not too complicated. Let's think about this triangle. Let's think about this triangle. I have drawn a exterior angle bisector meeting the extension of AJ here at point IA. I'm going to apply the exterior angle bisector theorem. What does that theorem say? Do you remember? It says JIA divides AIA equal this one. BJ divides this one, BA. What is the length of BJ? It's the angle bisector, right? So it's BC cut into portions of B plus C. And I'm going to take the left-hand side, the C portion. That's BJ. And then what's BA? That's simply C. Crossed out. So that's A divides B plus C. So it's essentially saying that this part is A, and then this part is B plus C minus A in terms of ratio. Okay. And that this directly gives the AJ divides AIA, the long leg, equal what? This one, B plus C minus A divides the whole thing, B plus C. That's what we want to prove, right? And that's it. And so it's correct. All right, we proved it from a complete different perspective, but everything still holds. Interesting, no? Right, the X circle has a lot of interesting things that relates to area approach, something worthy to think about. All right. Okay. Have fun. I will see you next time.